Hello, my name is Arash Mahnan, and I'm going to talk about real-time voice activity detection system using neck-mounted accelerometers. Before starting the presentation, I'd like to start with the disclosure. The funding for this project came from MinDrive, CTSA, and R1. Current voice activity detection systems use microphones. Microphones are not functioning properly with background noise, and they are computationally inefficient. On the other hand, accelerometers are, at minimum, equally effective in detecting voice activities. In a low signal-to-noise ratio environment, accelerometers are more accurate and they are resistant to high levels of background noise. Current accelerometer-based systems use jugular notch as a location for placing the accelerometers, and they're not putting it around the neck. And most of the systems, they don't work in real time, and they detect the voice based on the loudness, not voice onset or offset. And finally, existing systems do not function well with the concurrent vibration around the neck. In our study, we recruited 3 males and 3 females, healthy participants, and we recorded their voice. Our testing device included a 1-axis accelerometer, which was high sensitive to the movement and had 1000 Hz sampling rate. Also, we recorded the voice using Mix6 audio recorder. And for the test that we had vibration, we used lightweight encapsulated vibrators around the neck. One of the goals of the study was to find the optimum location for the accelerometer. We put accelerometer in 3 different positions: thyroid, cartilage, sternocleidomastoid, and C7 vertebrae. Also, we wanted to look at the effect of vibration. So we put 2 vibrators around thyroid cartilage, and we wanted to see how the acceleration data changes with vibration. For the experiment, we asked the participants to stay silent for 5 seconds as a baseline. Then we had a set of sentences for them to read for the with no vibration task and then with vibration task. During the test, we recorded both audio and acceleration recording, which were time synchronized. To measure the accuracy, we had 2 values. First one was number of onsets that we could detect, and second one was the duration of time voiced. We used the audio data as the accepted value, and we compared all the data from the acceleration to that. For the detection algorithm, we found the threshold using baseline. For that, we recorded the voice for 5 seconds in baseline, and then we divided that into subintervals of 50 milliseconds. After calculating the average power values for each subinterval, we averaged it over all the trials, all the subintervals, and then that value was the threshold. Then using the threshold, we introduced a 250 millisecond interval as a delay to the system, to the real-time system, and we used that 250 milliseconds. Then we divided the 250 millisecond into 5 50 millisecond intervals. After calculating the power on each of them, if 2 consecutive subintervals were the value of the power were higher than the threshold, then we detected the whole 250 millisecond as a voiced interval. Here is the result. As you can see, the algorithm works for just saying some words or even a continuous sentence. It can clearly detect a voice, and the interval length is appropriate. Also, when we look at the effect of vibration, if a vibration creates more noise, and it will create more error to our system, but still the data is promising. Finally, by looking at the location of the accelerometers, we can see that thyroid cartilage has the highest accuracy for both with vibration and without vibration trials. Since thyroid cartilage was found to be the optimum location for accelerometer, we can implement that into the wearable device that has been designed for treatment of the voice disorder spasmodic dysphonia. Thank you.